Hello, this is Engineering 211 Statics, and we'll get into some introductions here in a moment and talking about how the class is going to proceed and so forth. So, by way of introductions, I am Mark Miller. I teach engineering here at the college. My contact information you'll find on the syllabus, and we'll talk more about that, but there I am. There's my phone number. Probably a much better way to get a hold of me is by email. This web address here, if you're interested in studying engineering, that's probably a good address. Probably most of you are past that. More interested in where do you find these class materials and whatnot. Well, so I'll send you to a different website. Now I'll flip through these fairly fast, and some of them may be kind of hard to see on the video, but I'll be posting on the website not only the video but also the PDFs of these. What I'm writing on here, I'll make a PDF of and post that, so that should make things a little easier to see. Well, as I was saying, the website with the material is here. I have a personal website that is a Google site. Okay, so it's right there. That's it. If you just Google Miller Engineering LLC and sites, then it usually pops up. So there's the address, and if you can use the pause button, go back and grab that thing. I'll try and put it up in the comments of the video also. If I remember to do that, I'll try and do that so you can link to it there also. Well, when you click on that, it will take you to this website, and a few things here. A lot of times you'll be going to the Engineering 211. That's statics right there, so you'll go to that. This and that usually has some information and probably advising. We'll talk a little bit about what you might find in the advising link. And again, I realize this is kind of small, but when you get to the website, you should be able to see that. So before we get into statics, real quick, let's talk a little bit about advising. Make sure that you are in the right classes. If you go to this advising tab right there, there's a few resources, and one of them is this advising guide. If you've sent me an email or stopped by my office, I've probably given you one of these in hard copy, or if you've sent me an email, you've got a link to it. If you go to the website, you can get a link to it. This is certainly too small to read here on the camera, but gives you some idea. Multi-page handout talking about the classes that you want to take if you're going to Oregon State, Portland State, Oregon Tech, and so forth. I wanted to take one page out of that and look at that, and that would be the page for those going to Oregon State in civil, electrical, or mechanical. And that's not to say that if you're not heading to Oregon State that that's a problem, but it's just the majority of our students are heading to Oregon State in civil or mechanical or electrical. Now probably the electricals aren't in here, although if they are, that's probably a good choice. I think this class can be a good foundation for even electrical engineers, but probably mainly we have civils and mechanicals, and I realize you may have some environmentals or chemicals or something like that, and that's great too. I'm not trying to sideline any of those, but the majority of the folks in here are probably civil or mechanical. So if we look at fall term, your second year, this is your first year, this is your second year. So we're looking right here, fall term, your second year. You should have some classes there. If you're mechanical, you should have some classes there. And again, maybe a little bit small to see on the video. Grab the PDF and check on that. Basically, whether it's civil or mechanical, the list is the same. You should have EGR211, that's electrical fundamentals. I'll be talking to you in that class. Math 254, EGR 211, that's this class, and physics 211. Then there's a humanities and social sciences that can be worked in really any term. But these are the big ones. You got to make sure that you're in these. I believe all of those classes are only taught once a year, so if you don't get into them now, you won't get into them. A couple of things, be real careful on the physics. If you're in physics 201, that is not the class you want. You want the 211, you want the calculus based. So make sure that you're in those classes. Now, if you're taking this part-time or something like that, obviously maybe you've only got a couple classes, and that's fine. You're on a little different schedule. But if you're trying to get through this program in a couple of years, transfer to university, this is probably the set of classes that you need. So if you have questions with advising, talk to me during my office hours, talk to me during the lab period in here. We can get that hammered out. But most of you should be in those classes, so I just wanted to bring that up before we got going with the class itself. Well, speaking of the class itself, we're going to be doing this with the lectures videoed, so I'm going to put out roughly 3 hours of lectures. Probably not going to be exactly 3 hours because in the lectures I'm doing this in studio, so to speak, so I don't have a live audience with questions and whatnot. So I'll probably move through the material a little faster. So if you watch a 20-minute video and you stop it and you back up and you post some questions to yourself or others, it's going to take longer to get through. So the lectures that I'll post 3 of them each week. They'll usually be about somewhere around 30 minutes to 50 minutes. I'll try not to go any longer than that. So that's the lecture portion of the class, and then we have the lab portion of the class. And we're going to be meeting in lab for 2 hours each week, and that'll be a time that you can meet with me face-to-face. You can ask questions. I can try and answer those. You can work on homework. That's also going to be a time when we'll get together and take examinations. So we won't be doing online exams. You'll be doing the examinations during those lab times. So make sure that you take advantage of those. If you're saying, hey, I'm not sure about this lecture online, I like to be in class and get face-to-face interaction, make sure you're coming to the lab class. If you're watching the videos and it's working out great for you and the homework problems are going well for you, maybe you don't necessarily need to come to the lab class, although make sure you don't skip the ones where the exams are. That would be a bad deal. You can see where those are laid out in the syllabus. So with that, let's get started with statics, talk a little bit about where this fits in history-wise and things like that. If we put down some names here, certainly contributions by Archimedes. And hopefully that shows up. Yeah. When I say the video lectures, there's going to be the video of this on YouTube. Hopefully you can use the pause button and the rewind button and go and watch the portions that you need to over and over again. And then also I'm going to take, you'll notice that I'm numbering these pages. I'll take all of these pages and I will make a PDF of them, and you'll have access to that on the website too. Now you can do it however you want. I mean, if you're tired of listening to me and you just want to read the book, that's fine. It's up to you, whatever works for you. I think if I were a student, I would probably download the PDFs and maybe even print them out. Sorry about killing the trees, but print them out. And then as you watch the videos, you could add your own annotation, maybe in a different colored pen or something, to the PDF. So it's just a suggestion. So anyway, back to our history here. We had contributions to the body of statics by Archimedes. That was clear back in the BC years. Then Galileo, and of course Newton. Galileo was in the Archimedes, as I mentioned earlier, was in the BC years, about 200 BC. Galileo was in about the late 1500s. Newton was in about 100 years later, or the late 1600s. A gentleman put a lot of this together. It was before Newton's time, but put a lot of this together. And if we wanted to say, kind of who is the father of statics, didn't come up with the concepts, kind of put them together. There was a Flemish physicist or a military engineer, Simon Stevin. And he was around from the mid 1500s to the early 1600s. So that was actually before Newton. But a lot of the work that was not necessarily pulled into one body from people prior to Newton. He came along and put together in terms of statics and hydrodynamics and things like that. So if you're going back in history and you see names like Archimedes or Galileo or Newton or Stephen, those are all names related to this. When we think about how this fits into science, certainly it's under the umbrella of applied science. If we look at rigid body mechanics, and we'll talk very quickly about what it means to have something that's a rigid body, we would break it into two areas. We'd break it into statics, and we break that into dynamics. It can be very difficult to study dynamics without having statics, so this is a foundational class, a very important class. And in fact, as we start to look at things that deform clear up to the point where we get into fluids and talk about fluid statics and fluid dynamics, this is going to again be foundational. So hopefully we'll build a good foundation in here as we use this material not only to study things later this year, but throughout your education and your career. So I wanted to give you some names in there. Make sure I got those spelled close to right. I think so. If I talk about some basic concepts, maybe I'll put that on another page. So some basic concepts. So that's your ideas. The first one is the notion of a particle. So there's going to be some terms we use throughout this term and our studies going forward. And I want to make sure that we're all on the same chapter or boat with this. We'll say that a particle has no size. But has mass. Okay, so I probably have to apologize to our physics friends. They may not like that. It has no size, but it has mass, and it's going to be what we call an idealized body. Idealized body. Okay, that's where engineers will take maybe an automobile, and we'll look at it as a point at its center. So we'll take this and we'll analyze it as a particle of the same mass of the automobile, like that. Okay, a classic joke about how an engineer approximates a horse as a point. But we'll do that. And it works pretty good. If your automobile is zipping down the highway going north or south, it is a pretty good model. If it starts to rotate about its axis, so it's not only translating, going north or south, but also spinning, as if it were on ice or something, then it's not a very good model, and we'll have to come up with a more robust model. But we can do a lot of good work with the concept of a particle. We can get a little more creative, a little more complicated, and talk about a rigid body. With a rigid body, it's made up of particles. Made up of particles, has dimensions and mass. Okay, and the distance between the particles is constant. Okay, and that's actually important. This is where we think of the, you could think of a wireframe model where you take these points and you put them together with this wireframe like that, and we can start to build up something. And it's important that these distances between these remain constant. When we come over to these points, if we were to apply a force onto this one, this distance here, that distance there, is not going to be changed. It's a rigid body. It does not deform. And we're going to use that model for the first two terms here, statics this term and dynamics next term. Then we'll release that model and we'll actually look at elastic bodies, deformable bodies when we get to strengths and materials. But the rigid body approximation, the rigid body model is going to work well for us for a couple terms here. I want to talk also about a concentrated force. Now, like I drew here, we'll say that this is a force at a point. Okay, so let's say that we have a tire or something like this, and we've got some force applied to that. We know certainly with a radial tire that maybe deforms, that force is going to be acting over an area. But we're going to think of it initially as a concentrated force. We'll talk later on in this term about distributed loading, but we'll get started with our work talking about a concentrated force. You could model that as if you would have the unfortunate accident of stepping on a thumbtack or something, that thumbtack is acting basically as a concentrated force. Now if you want to really get particular, you can say, well, even the point of a thumbtack has area, so that's acting over area, and that's probably true. I mean, we've got people engraving the Lord's Prayer or something on the head of a pin, so that even a small area does have area. But when we start to compare this to larger areas, we could think of even a tack or a pin or something as basically being a concentrated force. Certainly, if we were to look at a steel wheel on a railroad track or something, we would see this concentrated force probably a little more easily than we might see with a rubber tire or a radial tire or something like that. So we're going to look at force at a point for a while, and then we'll go on and make our work more robust and start to look at distributed loads. Well, some of the other things we need to talk about is we need to talk about some basic laws. We're going to turn to Newton's laws. So with Newton's laws, and you can look these up in your textbook. You probably find them in your physics textbook. You can find them in the statics book. They're usually around the first part of the book, around page 5 or 6, depending on what edition that you have. These are the laws that Newton published in the Principiate. They were published in Latin, in the Principiate. And I may not be saying that quite right, Principian possibly. My Latin's not what it should be, but that was about 1687. Okay. Newton came up with the three laws, and your author has a nice explanation of them. I'm not going to spend the time writing them down here. You can look in the textbook as well as I can. But the first law says that a particle originally at rest or moving in a straight line with constant velocity, and that phrase is actually encapsulated in commas, so we could actually read the statement properly without it. It says that a particle originally at rest tends to remain in this state provided the particle is not subject to an unbalanced force. Okay. What about the business about our moving in a straight line with constant velocity? If it is moving along and it's not accelerating, okay, so if it's moving with constant velocity, it's not accelerating, and it's also not going around a corner, so it's not changing direction, so therefore it is, again, not experiencing acceleration. The first law says it will remain that way unless acted on by an unbalanced force. Okay, so what this really gives us is our first glimpse into statics, that if there's no unbalanced force, if I have something like this and I have a force here, F1, and I have a force here, F2, and those are the same, it's not an unbalanced force, and it's not going to be accelerating. It's going to remain that way, right? if you take maybe the chair that you're sitting in and you look at it, you're not accelerating up or down because while you're pushing down on the chair, the floor is pushing up on you. Those forces are balanced, hopefully, and you're not accelerating up and down. This gives us the equation that we'll be using eventually in equilibrium, where the sum of the forces is equal to 0. That's our nice equilibrium equation. Now, if we want to deal with acceleration, we can go to the second law. And again, your author has a nice expression of this. A particle acted on by an unbalanced force F experiences an acceleration A that has the same direction as the force and magnitude that's directionally proportional to the force. It's not the same as the force, but is proportional, and it's off by a factor of the mass. So the second makes this more interesting. It says, well, what if it is accelerating? And we come up to the equation, well, the sum of the forces is equal to mass times acceleration. And you'll notice on these forces, I've used this vector hat. When we get to chapter 2, we will talk about what that all means. So the force, the sum of the forces, is equal to mass times acceleration. So now if I have something like this, and I have a force acting on it, and it's an unbalanced force. It's not like this one up here. It's unbalanced force. What's going to happen to it? It's going to experience some acceleration, isn't it? And that will be proportional based on the mass of the... So there's the first and second law. Then the third law is to say, and your author has a nice statement of that, that the mutual forces of action and reaction between two particles is equal, opposite, and collinear. So if we look at you standing or sitting, people are pretty comfortable with your force acting down, but they don't necessarily like to think about the other force acting up, this normal force maybe pushing up. And if you're to not be accelerating up or down, we know that these forces are equal, that this force down has to equal this force up. They're opposite. This one is pointing down, that one's pointing up, and they are collinear. They are in a line. If they're not collinear, you're going to start to rotate. Wouldn't be good because we haven't got towards the latter part of the term yet. So probably the third law is the one people tend to overlook. They forget about a force or something like that. We're going to have a mechanism called free body diagrams that helps us account for those carefully. But we want to remember all of these. And in fact, if we could apply these three laws unfailing to all our mechanical systems, we really wouldn't need this year of mechanics classes, the three terms that we're going to do. So what we're going to do much of these three terms is practice these. Certainly the first two terms, at least, we're going to be practicing using and applying these laws. So make sure you look over those. They're in chapter 1 of your textbook. I'm sure they're in your physics textbook. We're going to be applying and using these on a daily basis. Well, the last thing that I'd like to get into today before we get set to do vectors when we get together next time is talk a little bit about the units. So we have dimensional homogeneity. There's a big term. Which, if we look at that, that really just means one unit. We oftentimes use the example, if I have some sort of a cube where I have 24 inches and 2 feet and then 2/3 of a yard, it would not make any sense at all in finding the volume of that to multiply 24 times 2 times 2/3. You'd have a mess or a hash of the units. So you need to get a consistent unit, a single unit. So we might change this to 2 feet. We might change this 2/3 of a yard to 2 feet, and then we'd have 2 feet times 2 feet times 2 feet, and we could then get the answer. What do we have there? 8 cubic feet. Okay. So you might say, well, that's pretty simple. I can't believe you're talking about this in a second-year class. Well, this comes up and bites you. You know, we'll have problems where we have feet and inches mixed or pounds and tons mixed, and it will come up and bite you. So be really, really careful of that. Now, while we're talking about units, We might talk about a little bit about units of force and mass and different systems. So let me talk about the unit system that we're going to talk about. We can talk about the SI, Systems International, or sometimes called the Absolute, and the English, or the what's known as gravitational. Okay, and if I look at fundamental quantities here, fundamental quantities under the SI system would be mass and length and time. And there's other quantities, but those are the ones that we're going to be most interested in this class and today. And under the English system, the fundamental would be force and length and time. And then we get the derived. And under the derived quantities, we would then derive force. And under the English system, we would then derive mass. So let's see how that works. If I go and look at Newton's second law, force is equal to mass times acceleration. I'll write that over here. Force is equal to mass times acceleration. I could, for the metric system, say that 1 Newton is equal to 1 kilogram times 1 meter per second squared. So I get then that a Newton is equal to a kilogram times meter per second squared. And those of you that have done some physics probably recognize that right off. Well, what about the English system? Well, here with the English system, I would say that 1 pound would equal 1 slug times 1 foot per second squared. And then I solve for the slug, because here in the metric system I solve for force. This is force. Here I'm going to solve, in the English system, I'm going to solve for mass. I'm going to solve for that slug, which is mass. And that would be that a slug is, let's see, a pound times a second squared divided by a foot. Did I get that right? Slug is equal to a pound, second squared, yes, over a foot. So a pound times second squared over a foot is a slug, and we've derived the mass quantity. Of course, popular culture tends to confuse this quite a bit. If we go to maybe buy something, coffee beans in northern Washington, we would buy them by the pound, wouldn't we? Which is a force quantity. And then we go to southern Canada, and we would buy them by what? The kilogram, which is actually a mass quantity. Now, since the acceleration of gravity didn't change significantly, probably from northern Washington to southern Canada, we're probably okay with that. But those are confusing terms. One is a force term, one is a mass term. And when you get into situations where your acceleration of gravity is going to change significantly, for instance, as we travel from here to the moon, our mass here and our mass at the moon should be the same if we don't eat or exhaust anything along the way, whereas our force, or our weight, weight's just a special category of force, is going to be quite different when we compare our weight or our force here versus that of the moon. So we have to be careful of that. If you get into doing inertial navigation or something like that, even there's differences as you go around the globe, as going over mountains or over big trenches in the ocean or something like that, the acceleration of gravity will change, and you have to be careful with that. So I wanted to point that out. We've talked about this in the past in some of the GE classes. If you weren't around then or you forgot it, we're going to use both of these systems. You're going into engineering in the U.S., so you have to be able to deal with both systems. You'll be dealing with medical people that deal in the metric. You're dealing with other countries that deal in the metric. Most of our work is still around here in the English system. So you got to deal with both of these, and I wanted to point this out. Now, where we're going to go next is we're going to look at vectors. So We're going to look at vectors. So why am I putting this odd hat on a vector? We'll talk about that, how we indicate a vector, what a vector is, compare it to a scalar, and that's going to be Chapter 2. So if you're following along in your textbook, we really completed the quick introduction of Chapter 1 with this lecture, and we'll move on to Chapter 2 with vectors. So thank you for watching, and I'll see you next time. Take care till then.